We're going to continue taking a look at optimizing volume and surface areas. For our first example, we're going to include a restriction. So Adam is designing a candle holder. It'll be a rectangular prism with an outer surface area of 225 centimeters square, a square base, and an open top. We're going to look for the maximum volume. And remember, we have a square base, so that means the base has the same dimensions because it's in the shape of a square. However, our height will be different or may vary. This one will not end up looking like a cube, so we're going to use a table of values to determine what shape we will have. So we're going to pick lengths. So I started with a cube root approximately of 225 as my starting point. So I'm going to start with 6. And then I'm going to find the height using this formula, which I'm going to show you how to get right now. And then using the volume of a cube, which is length times width times height. So this one is L times h, so L squared times h. We can now complete this table. So how did we get the formula for height? First of all, I examined the surface area of the box we have from above. So remember, the surface area is the area of each of the rectangles in that picture. The base of this is length times length, so that's L times L, which is L squared. And then there's 1, 2, 3, 4 sides, plus 4 sides that are length times height. Length times height, and the base is length times length. Our surface area is 225. We want to solve for h, so first I'm going to minus the L squared from both sides. So I get 225 minus L squared equals 4LH. And again, we're isolating for h, so I'm going to divide out the 4L from both sides. So we get 225 minus L squared over 4L is equal to h. And that is the formula we have right here. So using your calculator, let's determine the heights for the lengths that I've included, 6, 7, 8, 9, 10, and 11. So try this yourself, then determine the volumes, then come back and check your work. So remember, we're looking for the maximum volume. And we see that our biggest numbers are 322 and 324. So I'm going to assume that number is somewhere in between 8 and 9. So we're going to continue and look at numbers between 8 and 9. So what I'm going to do is go downwards from 9, because I see that 9 is definitely higher than 8, and see if it gets any higher. If it gets lower, then we try 9.1. But let's go from there. So let's start at 8.9. Right, so 9 is what we think is the max, but let's check. So 8.9 gives me 4.095 for the height, and then when I look for the volume, I end up with 324.4. So it's a little bit higher. Then I go to 8.8, I get 4.192, which again gives me 324.6. So again, a little higher. Let's try the next one, 8.7. That gives me 4.291 roughly, and this gives me about 324.7 or 0.8 if I round. Let's see what happens with 8.6. 8.6 gives me 4.391, and when I calculate this one, I get 3.24. I get 324.7. So we can see, if we continue, that we can even find a better result. And notice how this is almost a 2-to-1 ratio of length to height. Similar when we did areas and perimeters and we removed a section, the same thing happens with a cube if we remove a piece. So it looks like our length is 8.7 and our height is 4.3. So we're going to have a rectangular prism that's 8.7 meters wide and 4.3 meters tall, and then the base of this again is 8.7 meters, and this should maximize the amount of space inside this holder. And notice again that the lengths are approximately double the height. And sorry for the mistake there, these should be centimeters. Alright, next one. This time we're not going to look at a cube, we're going to look at a cylinder. So if you were to get a question like this, I'd guide you on what type of values you should use. So what is the minimum surface area for a cylindrical can containing 350 milliliters of liquid? The first thing we should note is that 1 milliliter is equal to 1 centimeter cubed. So that means that this here is 350 centimeters cubed. Since we're looking at a cylinder, we are looking for the dimensions of the radius versus the dimensions of the height. So we're going to pick our radiuses to start and see if we can find what can design will give us the minimum surface area. So how did I get the height? Well, since we're given the volume, remember the volume is pi r squared h for a cylinder. We're told that 350 is our volume. And if I want to solve for h, I got to divide both sides by that pi r squared. So they'll cancel out. And then we're left with h equals 350 pi r squareds, which is what I put in for my formula for the height. Using this formula and the given radiuses on the left, let's figure out the heights for those radiuses. So now that we have the height and the radius, let's figure out the surface area to create that can. And we can see the smallest one we get is 275. The next closest one is 289. So we're going to look at 4, see if it is the min, but what we'll do is we'll go down from 4, try 3.9, 3.8, and so on, to see if we can get any smaller. So let's try some of those. So next let's go to 3.9. So if I type in 3.9, when I go to find the height, I end up with 7.325. And I end up with a surface area of 275.05. So it looks to be a bit bigger, but I didn't round my first one. This was 275.53. So it is a little bit lower. Let's try 3.8. 3.8 is 7.715. And that gives me 274.94. So again, it's a bit lower. So let's try 3.7. That's 8, sorry. 0.138. And when I try this one, I get 275.21 approximately. And we can see we did hit the lowest one about here. So radius of 3.8 and a height of 7.7, which is interesting. If you look at this, it's a radius of 3.8 and a height of approximately 7.7. If you double that radius, 3.8 times 2 is approximately 7.7. So this can would be almost in like a cube shape, which if you think about it would give you the minimum surface area but the maximum amount of space inside. And there are 4 questions for you to try.